We've already seen SN2 reactions, and you know that the mechanism goes through one only step in where the nucleophile, in this case this acetate, will attack the electrophile, this carbon right here that is electrodeficient, and the leaving group would leave. So we remember that we always draw these curved arrows with a full arrow at the end, and so this is how we show that where the electrons are going from this electron density here in the oxygen that has a negative charge to the electrophile. So nucleophile to electrophile. Remember, I told you, if you know and you're able to identify these electron flow, you have all organic chemistry or most of the organic chemistry courses under control. So this is going to be a little repetitive, but as we saw in the previous video, SN2 reactions are called SN2 because they are second order kinetics. What that means is that it's a bimolecular reaction in where the alkyl halide right here and the nucleophile concentrations will be included in the rate. This is also a repetition from the videos that we saw for chapter 6, but for the energy diagrams of SN2 reactions, they are always going to look like this. It's going to be one hump in where we have our start materials, then we have the transition state. Remember, the transition state is indicated between brackets and with this sign right here. And here we see how the nucleophile is approaching. So at this point, we don't have a fully negative charge. We have a delta minus that is approaching the carbon that is electron deficient. And the other delta minus is here at the BR, right? Delta minus, delta plus, delta minus. And then we have the products right here. Remember that we can identify some elements. This is going to be a review from chapter 6. We have the activate energy that it will take to go from the start materials all the way up to the transition states. And then we can also identify this energy difference here, which is the energy difference between the start materials and the products, and that is the delta H. That's the enthalpy. So in theory, the SN2 reaction could happen in two different ways. One, that the nucleophile attacks from the front, kicking out the BR, and that will be called the front side attack, or the back side attack, in where the nucleophile attacks from the back, kicking out the BR. Well, this front side attack doesn't work because of sterics. So think about this nucleophile being big, attacking a BR which is already crowded, right? So this side of the molecule is already crowded. This reaction is simply not going to happen. But if this were to happen, the nucleophile will end up being at the same place where the BR was, right? So that the stereochemistry will be conserved. So whatever this chiral center would look like, it will be conserved at the end. However, what it actually happens is that we have a backside attack, and I mentioned this in the previous video. In the backside attack, the nucleophile attacks from the completely opposite side from where the leaving group is, so that it will attack at 180 degrees, because by attacking here, it can kick out with the highest impulse force, whatever you want to call it or you want to imagine it, that leaving group. So the backside attack will be 180 degrees from the back of the leaving group, and so that results in what we call an inversion of configuration. So what will happen is that in this case at the top, the nucleophile will end up where the BR was. And here, the nucleophile will end up in the complete opposite situation where the BR is. And so what ends up happening is that the nucleophile replaces the BR, but on the opposite side. And I'm going to talk later on what are the consequences of that. So, as I said, if we get a front side attack, this will be the product. So the nucleophile will end up being where the leaving group was. So imagine this is what we started with, the H, and here we have our leaving group, right? So if we do a frontside attack, this is what you would get, but what you actually get is this one. So that is not happening. And what happens is an inversion of configuration. What is an inversion of configuration? And so again, this nucleophile attacks, and this is my transition state, and then that leaves. When that center inverts, what it means is that if you start with an R center, you will end up with an S center, and the opposite is true, right? So here we have a couple of examples where the SH minus attacks here, kicking the iodine out. And so remember that iodine already has 3 lone pairs. And when it leaves, it also takes these lone pair here. So that's why we end up with a minus. And the hydroxide attacks, kicking out the Cl. So if the Cl was on a wedge here, the OH will be on the dash. And here, so it stays in the plane, right? Because the iodine is on the plane, and so the SH is in the plane. But imagine that this SH is not attacking. So imagine I have my iodine here, and here I have an H, and here I have that. So if my SH minus were to attack this center, what would happen is that the methyl will go to the back and the SH will become the front one. So just as SH, and here will be my methyl, right? So there's an inversion of configuration. And does the substrate matter for SN2 reactions? Yes, very much so. The way that we look at it is the less substituted my methyl, my substrate is, the easier for an SN2 reaction to happen. So if my alkyl halide is not crowded, such as the methyl one, this one right here, the primary, the secondary, the tertiary, these ones will be easier. For these ones, it will be easier to undergo into an SN2 reaction. Imagine this. So we have, these are all hydrogens right there, and here I have a Cl. So when a nucleophile comes and attacks, you see these hydrogens are not too big, and they are not on the way of my nucleophile attacking and then the leaving group leaving. But if we go to the other extreme, imagine you have, so I don't know, a big ring here, and here you have, I don't know, maybe a chain, and here you have another big molecule, and here finally you have your leaving group. So let's try again. So here I have my leaving group. So if the nucleophile tries to reach here, it's going to be hard because it's crowded. So the less substituted my substrate is, so a methyl, primary, secondary, the better for SN2 reactions, because these ones are sterically hindered and these are less sterically hindered. Here you can see how these electrostatic maps express or show how the nucleophile is going to be more and more sterically hindered as we increase the size of the alkyl. So if we keep the bromine being the same for every single case, the nucleophile in the case of the simple methyl is much less hindered than it is on a primary, secondary, or tertiary alkyl halide. So today's class code is going to be 4, 7, 8, 5. And this is a summary of the characteristics of an SN2 mechanism. Remember that SN2s are called SN2 because they have second order kinetics. So that means that the rate is going to be defined by this expression right here. So some of the questions that you may be asked is, what would happen if you double the concentration of your nucleophile? So you can see that it will double the rate of your reaction. The mechanism happens in one step. Remember that it happens through a backside attack that results in the inversion of configuration of the stereogenic center. And the identity of R, meaning the start material, matters. So the more unhindered it is, so the less hindered it is, the better for SN2 type reactions. And so here I'm going to show you two examples of real life applications of these SN2 reactions. They are very much used in a lab in organic chemistry. So let me just show you. So the first one, we have a nitrogen here and a nitrogen here, and you see that they are going to end up connected by two carbons in the middle. Those two carbons are going to come from this molecule right here. So this is one of your first exposures to real life reactions. So nitrogen is going to attack my electrophile right here, and Cl is going to be my leaving group. On the other side, the other nitrogen is going to attack this carbon, kicking Cl as my leaving group. So let's just show that. So the first one will go here, the Cl is out, the nitrogen will come here, and then the Cl is out. And so that will result in this molecule right here. The second step, very similar. We have the electrophile here, leaving group. The nitrogen will attack and the leaving group will leave. And then we'll get this molecule that is just one step close to Prozac. But I don't know if you noticed that this nitrogen right here carries two H's and this nitrogen right here just carries one. And the reason for that is because we are missing one last step that is very important. So just to simplify what we had over there, we had a molecule, an alkyl halide that had an iodine, and then my nucleophile was carbon, sorry. So it was carbon, nitrogen, that nitrogen was connected to two H's and that carbon was connected to three. And the nitrogen has a lone pair available, so that's going to be my nucleophile, electrophile, leaving group. Always look for these three elements. These will come, attack, and leave. And the result of that will be the nitrogen is now connected to the H, and the CH3. But be careful here because that nitrogen should have a positive charge because it's connected to four things. So now the second step, so remember we have iodine here, and the second step is that iodide could come and get this hydrogen or any other base that you have in the reaction that could come, and that is what we call a proton transfer. So the second step is what actually gives us the product, right? So because the substitution happens first, and then, so I have a hydrogen, I have the R, and then I have the CH3 and the lone pair, right? So plus HI, for example, or whatever base that came and get the molecule deprotonated, right? So that is the molecule that you want, and it happens in, even though the substitution reaction happened in two steps, you have to add this second step, that is the proton transfer. And you're going to see it very often. We cannot end up with a positively charged molecule.